Hello, welcome to my talk. I am Art Gower from the University of Sheffield, and here are some of my collaborators. I want to talk to you about waves scattering from particulates, random particulates. But first, have you ever heard of the company Theranos? Well, they started 10 years ago with the idea that with one tiny drop of blood, maybe they could do all the same diagnostic tests that you could do with like liters of blood. And they were going to revolutionize the field of diagnostics. For their startup money, they managed to raise $700 million. Think about that next time you apply for a grant. But it turned out it was all hype. There was no science. It all failed. They got nothing from it. There's a documentary on Netflix, and I highly recommend you watch it. But here, similar to that, here's my pitch for a company. I only want $100 million, not $700 million. My idea is this. Imagine this droplet of blood on the right. What if we can perform tests on the droplet of blood without diluting it, just as it is? We'd send in a wave, let's say electromagnetic or sound. Back would come something scattered, and from that scattered wave, what if we could learn about the particles in the droplet of blood? What if we could learn about this material without diluting, filtering it, centrifugation, and all these things? And that's basically the theme of my talk, and I will be accepting donations at the end. So this sort of idea is used for many particulate materials in industry today, including oils, suspensions and emulsions which mix water and oil, porous material which mix air and solid, and powders which are solid particles in air. And you can use all kinds of waves to try to measure their properties or statistics, because they all have the same sort of wave equations with linear boundary conditions. So how would a measurement work? This is the idea of it. You put in some sources, some sensors, and you try to measure what comes out. But we don't want the measurement to depend on the random position of particles. So in a lab, you take a measurement many times and take an average. In maths, the way you do it is you set a certain position of the particles, calculate the scattered field, then you choose another position of the particles, calculate the scattered field, and then you just do that over and over and over and over again, and you get the average. And this is what the average looks like. It's called the ensemble average, and you can do this in an experiment by taking the average over time or space. And one of the neat things to do in this is, like, now that we've got this sort of averagey field, rather than trying to do all that complex maths, can we just replace the material with a homogeneous, effective medium? People love to have an effective density and effective sound speed. But I bring a message of doom. If you were to try to do this with two materials of different shapes, like this one on the left, a rectangle, this one on the right, a circle, and you were to try to calculate the effective density and sound speed, with lots of different techniques, we can argue about which techniques, you will conclude that they are not the same. Even though the microstructure is the same for these two materials, the same kind of particles, their effective densities and sound speeds are not the same, except for low frequency, very low frequency. On the other hand, they do share something in common. They share what I call effective wave numbers. And the reason that you don't get the same density and sound speed is because this process of averaging creates quite complicated boundary conditions, which are not the same as a homogeneous material. I'm going to talk you how to get there and explain about techniques to calculate average scattered fields. So we consider that there's a scalar wave equation in the host material and a different scalar wave equation inside the particles. We describe the field scattered from one particle with a sort of series expansion of special functions Vn, where the f's are the unknowns. These Vn's have different special functions which depend on your dimensions. In 2D, they're Hankel functions with Fourier components. In 3D, they're spherical Hankel functions. And they're also different if you use vector wave equations. The last component you need to follow this method I'm going to teach you about is that you also need something called a scattering matrix, which relates the incident field coefficients, these GNs, to these FNs, which are the outgoing scattered coefficients. Once you have that, you can now follow this recipe I'm going to tell you about. First, you need to ensemble average the particles. To do that, you give a variable name for the center of each of the particles, x1 for the first center of the first particle. You assign a probability for them occupying a certain configuration, probability function, and then you can average any field just by multiplying it with the probability function and integrating over all possible positions of the particles. If you had particles of different shapes and orientations, you'd also have to integrate over the orientations and shapes. So for example, if I took the total field u that equals the incident plus the scattered field from each of the particles, now we have a sum over j because each j is a different particle with a different center. We can average this equation by multiplying on the left and right by the probability density and integrating over all particle configurations. And once you do that, what you'll find is that the particles become indistinguishable because each of these particles have been integrated over all their possible positions. So the sum over j disappears and just becomes capital N, which is the number of particles. The whole sum just disappears, and because each of the things summed becomes the same. So that's a nice magic trick. A very large sum has been replaced by just an integral. And in this case, this average f I've just used to describe the conditional average of this scattering coefficient, which is the thing we want to solve for. That's a technical detail, but we're looking to solve for this. And we can solve for this by applying this same technique of ensemble averaging to the boundary conditions of all the particles, and you reach this more complicated thing below. But the main message here is that you've got something related to the incident field. Here's the domain of integration, something related to some special functions Vn, that's this u, this convolution integral, and the unknowns are these average fields Fn's, which describe something about the scattering coefficients. The domain of integration is this big R here. This big R here is just the geometry of the material. So if you want to do a sphere, this would be a sphere filled with particles. But you have to exclude from it this ball B with radius 2r. You can see it's excluded here. And that's because when you're integrating all possible particle positions, you find that the particles cannot overlap. And that translates to excluding this ball from the integration. There's currently a few things known about this solution, but I want to talk to you about what's not known, and that's a general strategy to solve this and reach sort of general conclusions about materials or particulates. And to do this, we take inspiration from previous solutions. We just say that the average field, Fn, is a sum of some unknown fields, but each of these unknown fields satisfies a wave equation. That's the trick. That's all it is. You're trying to solve for this Fn, and you say it's a sum of unknown things, and each of them satisfies a wave equation. And surprisingly, that leads us to exact solutions. How does that work? I'm glad you asked. I would love to tell you some more. And this is how it works. You basically, when you've got an integral, and inside the integral are two things which satisfy two different wave equations, there's a very well-known trick to rewrite this volume integral. You can just use the fact that they both satisfy the wave equation to rewrite them as such. Pause the video if you want to prove that yourself. Then you can apply, once you have it in this format, you can apply Stokes' general theorem, or you might know it as Green's second identity, to rewrite a volume integral in terms of a surface integral, as so. In this case, we get two surface integrals, one over the surface of the material and one over the surface of this exclusion ball. Very interesting. Why? What consequence does that have? And it turns out then that the results of these components now satisfy different wave equations as well. Haha. With a Bn from the incident wave satisfying a wave equation with wave number k, and the integral over the whole material satisfies a wave equation with k, and the others satisfy wave equations with wave number kp. That allows you to split this equation into two separate equations. So these two equations are very cool now that they're separate. The first one I call the ensemble wave equation. It depends only on the microstructure, on the statistics of the particles, and not to do with the incident wave or the geometry of the material. The second one depends on the incident wave, the Bn, and on the geometry of the material, so I call it the ensemble boundary conditions. The first one is a Friedholm integral equation which you can solve for the Fpn. There's an F inside this too. And what that allows us to do is we can now solve for things like the effective wave number, in general, without naming what the incident wave is or the geometry. So if we substitute a general series expansion into the first one, you can formulate an eigensystem for these eigenvectors f and the effective wave numbers kp. Very cool. And this all comes from that ball, the exclusion zone, which doesn't depend on the geometry of the whole material. And it works for all materials, and it reduces to the plane wave case, among others. And here are some effective wave numbers for you to look at. Okay, but that's just effective wave numbers. How about we now try to specialize this to a sphere filled with particles, like in the beginning, that droplet. Well, the eigensystem from the general wave equation is still the same, but we can specialize the boundary conditions to the case of a sphere with little particles in it. And just to make a note here, these boundary conditions are not the same as a homogeneous acoustic sphere, and that's why the effective density in sound speed doesn't really work well. So here it is, our sphere. It asks, do I have effective properties? I'm afraid you don't, but you do have effective wave numbers, which are valid for every geometry. This is what the solution looks like for one frequency omega, and this is the absolute value of that scattered field. If we were to compare that with the absolute scattered field from a homogeneous sphere with the effective properties rho and c, these were calculated in the best method possible, you can see that they're clearly different, and that's the key point there. So why care? Well, first of all, reach some beautiful equations. We've managed to reach a separate sort of equation governing the effective wave numbers and another equation governing the boundary conditions. It works for every geometry, although there are some details involved if your geometry is not convex and has sharp corners. We haven't really addressed those issues. We need efficient solutions for the inverse problem, and that's for my startup. So we need help in solving this to be able to learn about this droplet of blood. These sort of equations are also really important to help design materials, to have sort of general sort of conclusions about the wave numbers and the microstructure and how the microstructure translates to effective wave numbers. And here are some references, and it looks like I've finished my talk with a minute to spare. So thank you for listening.